All right, people. We're going to talk about molecular shapes and molecular shapes you need to know for high school chemistry. What the names of the shapes are, what they look like in real life, and why they look that way. And it's pretty simple stuff. Now, if you're in North Carolina, these are the shapes you need to know, and maybe other states as well. If you're wondering where this accent comes from, we're in North Carolina right now at the beach near Topsail Island. So here are shapes: linear, several different types of linear, trigonal planar, bent, tetrahedral, trigonal pyramidal, and octahedral. I'm going to build all these for you. I'm going to explain to you why they have those shapes. If we look at the upper right hand part of the periodic table, you should know the oxidation numbers of these. This one, it's +3, and then carbon plus or minus 4, nitrogen's -3 oxidation, oxygen -2 oxidation, fluorine -1 oxidation. And, this group doesn't do any bonding, so we don't have to worry about them. Now, what this means is fluorine has 7 valence electrons and it needs one more. Okay, so when we talk about molecular bonding, all right, these charges, knowing these charges really help us, all right? Fluorine, and we have to include hydrogen also in this column. This group makes one sharing covalent bond. And the reason that is they only need one more electron because they have a -1 oxidation number. The oxygen group typically makes 2 sharing bonds. The nitrogen group, right, they need 3 more electrons. They typically make 3 sharing bonds. And carbon is always going to make 4. 2, 3, 4. And if we go back here and we look at boron, we can look below boron at aluminum, etc. And I don't talk about these much because usually when we're talking about these molecular shapes, we're talking about only things from the right side of the stairs, okay? But if you saw aluminum represented in a Lewis structure somehow, or boron, you'd be imagining it would have 3 bonds because these things tend to lose 3 electrons, all right? So these bonds here, these lines represent covalent bonds, and each one of these lines represents how many electrons? That's right, 2 electrons. So let's try to make some shapes and see what happens, all right? First, let's talk about the molecule hydrogen. Hydrogen gas. Hydrogen's one of the deadly 7. Hopefully your teacher's already taught you that, but this is a molecule of hydrogen gas. The formula is H2. We take a look at our sheet here and we see that hydrogens want to have one line attached to them. So if we make a molecule of H2, it actually looks like this if we're drawing it. Now, hydrogen only has an inner shell on its atom, so it only has 2 valence electrons. So I told you these lines each stand for 2 electrons, and the next thing I need to tell you is that if you draw a line between 2 atoms, that it represents a sharing bond of 2 electrons. So since they're shared, that line counts for this hydrogen and for this hydrogen. So they each have 2 and they're happy, okay? What shape do you think H2 would have to be out of these shapes? Well, it's obviously in a line, so this is a linear shape. And if we had to build it, we could just take a couple of marshmallows, because I like to build my stuff out of marshmallows, because then we can roast them on some Bunsen burners at the end of class. And this little toothpick is going to represent my covalent bond, and there is my linear molecule for H2. Boom. Now let's think about this. We have to talk about a new term called polarity. And polarity means, does the molecule have 2 different ends or not? Okay? Something that is polar has 2 different ends. Obviously, H2 has an H on end. It looks like this, has an H on each end. So this would be a non-polar molecule. And another thing I like to talk to my students about is dimensions. You can draw a line and lay it down on one plane. So that means something that's linear is two-dimensional. And your teacher may not like to talk like this, and that's fine. But a linear shape is a 2D shape. It's only on one plane, and that's going to come into play later. Let's draw another molecule. What if I drew something like, what if I was representing hydrogen chloride? What if I was drawing a Lewis structure of hydrogen chloride? Well, hydrogen needs one line, and if we look at our table here, we know that chlorine, boom, it's in this group. It's also going to only want to have one line. So guess what? Boom, we've got one line. But now we're not done. This hydrogen has 2 electrons here represented, so there's no more valence electrons. It's happy, but chlorine should have 8 valence electrons. So we need to put 1, 2, 3, 4, 5, 6, boom, 7, 8. Now this one looks correct. Yes, it is 2D, and yes, it is also linear. But what I would do for this, if I was going to make myself a nice marshmallow diagram of this, is I would use 2 different marshmallows, and that's going to help me. Because now I can ask you, is this 2D linear object, is it polar or nonpolar? Does it have 2 different ends? Yes, it is polar. This end is different than that end. There are more ways to have linear molecules than you may think. And here's another way we can end up with a linear molecule. Let's take a look at carbon dioxide. Now, carbon, if we look on our little shape sheet here, carbon wants to have 4 lines attached to it, and oxygen wants to have 2. So when we're drawing our pictures, we end up with something like this. We can put an oxygen on each end. And now this carbon has 4 lines attached to it, and each oxygen has 2, right? Now what's missing? Yep, obviously valence electrons are missing, and they'll be spread out like this. Why would they be spread out like this? That's right, because all the electrons are trying to keep away from each other. They're all repelled. So these guys would be sort of up here, keeping away from here. These guys would be like here, keeping away from here, and they're all keeping away from each other here too, so you end up with this sort of shape. Now this is a linear shape, and it's still 2D, it's still linear, and right here we see there's a double bond and a double bond. So CO2 ends up being a linear molecule, but not all molecules, or not all of these shapes end up being aligned when you might think they would. Let's take a look at something like, let's take a look at, say, oxygen difluoride, okay? If we were going to do oxygen difluoride, we'll have this little oxygen in the middle, okay? And we know oxygen wants to have 2 lines, right? And how many lines do the Fs want to have? They each want to have 1. Now you may want to be like, hey, boom, I'm done, but you're not. This is wrong. And the reason it's wrong is because you haven't finished your oxygen. You end up with a shape like this, and the oxygen, notice, it's got 2 lines, but there are still dots we haven't put on our picture. Look, this fluorine needs to have, right, 6 more dots. And now we can make up the whole valence of fluorine, 1, 2, 3, 4, 5, 6, 7, 8. This guy, 1, 2, 3, 4, 5, 6, 7, 8. And now this oxygen's only got 1, 2, 3, 4. Well, boom, 5, 6, 7, 8. Now these are pairs of electrons. The electrons occur in pairs. That's how we think about them. These unbound pairs, see, unbound means they're not connected to any other atoms. These unbound pairs, well, they take up space. Just like magnets like to push away from each other if you have them turned the wrong way, these electrons don't like each other. They push those atoms down. Everybody's trying to keep away from each other, and these guys are trying to keep away from each other too. So you end up with this shape like this. I'm not going to put the extra valence electrons on here. You end up with the shape being bent. And why is it bent? That's right, it's bent because of these unbound pairs of electrons, okay? That's why sometimes you end up with shapes that are bent. If your central atom, and the atoms that are in the middle, we call them central. If your central atoms have leftover unbound pairs, you're very likely going to end up with a bent shape, okay? Now, if this atom is the central atom, the one in the middle, then the ones on the outside, you may guess, take a guess. Yeah, the good word would be peripheral atoms. Okay, let's keep mowing through this. Let's take a look at, well, let me show you a bent molecule. Okay, here are my two fluorines. I'll use a big marshmallow to be my oxygen as the central atom. And boom, boom, boom. Can you think of another molecule that's necessary for life on Earth that may also end up being bent like this? Might have a oxygen in the middle and may have an atom out here that only wants to have one shared bond. Yeah, you could have two H's and an O. So water looks like this. Water is a bent molecule. All right, let's keep rolling. Now, sometimes we'll have, I don't know, how about 4? What if we had nitrogen trifluoride, trifluoride? First, we'd say, how many lines does nitrogen want to have? And we'd be like, yep, 3. It wants to have 3. If we're looking at our little chart here, nitrogen wants to have 3. And again, fluorine wants to have 1. So we can draw the shape like this. We got to take these fluorines. We have to spread them out because they're all keeping away from each other. Each one of these fluorines needs 3 unbound pairs of, I drew those wrong, but 3 unbound pairs of electrons, right? So now we have 8, 8, and 8. All our fluorines are happy, but is this nitrogen happy? Are all 8 valence electrons shown on here? No, they're not. There's an extra pair of electrons here. Now, what would that do? What it would do is it would take this picture from being this flat shape like this unbound pair being up on top would actually make this a little tripod that stands up. It would make this shape that seemed to be flat, this unbound pair of electrons would push these other guys away from it and warp the shape of this molecule. Now it stands up like a pyramid. This is a trigonal pyramidal shape. And why is it trigonal pyramidal? Well, this nitrogen has 2 electrons in its valence shell that haven't been accounted for. And those 2 electrons right here make a little area that pushes on all of the other peripheral atoms. So the central nitrogen atom has an unbound pair that pushes down on the other 3 atoms, and you end up with the shape that stands up. Now, sometimes you can end up with a shape like, if I was going to draw, if I wanted to draw this better, I like this. Now, your college professors might not like that, but I like for my kids to draw nitrogen trifluoride or a similar molecule like this. That way we can see that it's a pyramid, that it's got up and down. Now, look at the shape right here. This shape that I've made, does it have a top and a bottom? Does it have 2 different ends? Yeah, this is also a polar shape. And take a look at this shape. It's not 2-dimensional. It's 3-dimensional. It's a 3D shape. So if you were ever asked about how many dimensions does nitrogen trifluoride have, you'd say that thing's a 3D shape. Let's keep rolling. What if we tried to represent something that had a similar formula but was a little bit different? Like, what if I did aluminum fluoride instead, okay? Now, you may never be asked to do this because technically this crosses the stairs. It's ionic. Technically, aluminum fluoride will create a crystal lattice. But if I was going to represent this as a Lewis diagram, I could draw it like this. And 1, 2, 3, 4, 5, 6, boom. 1, 2, 3, 4, 5, 6, boom. 1, 2, 3, 4, 5, 6, boom. And now this aluminum is here. And you would say, well, now this thing's going to warp up, but it doesn't. Let's think about an aluminum atom. Okay, aluminum fluoride ends up being a flat shape like this, flat. And since it's flat, okay, none of the ends are different. There's not a top and a bottom. It just lays flat here, okay? It's a 2D shape, and since it's laying flat, all three ends are the same, okay? So aluminum fluoride would be only two-dimensional. It would be called trigonal planar. Planar means it's on the same level. And would this be polar or nonpolar? If I turn this around, could you tell that it had been turned? Are any of the sides different now? No, they're not. So it's a nonpolar shape, all right? And you may be like, Miss Teacher person, isn't there an unbound pair? Aluminum only has 1, 2, 3, 4, 5, 6. Well, let's think about this aluminum atom and how it started out. Aluminum would be 2, 8, and 5. Excuse me, 2, 8, and 3, right? Well, these three valence electrons on your 2, 8, 3 aluminum, on your 2, 8, 3 aluminum, these three electrons are the ones in these pairs. So this whole shell is accounted for, so there's no unbound pair. Do you like that? All right, let's keep rolling. Let's think about some other shapes. What if we had carbon tetrahedride or methane, all right? How many bonds does carbon want? Well, we know that carbon wants to have 4. And how many does hydrogen want? Every hydrogen wants to have 1. So I can just put this carbon here and spread these hydrogens out. Remember, they're going to spread out as far as possible. And I'm already done with this picture, okay? CH fluor looks like this. There are no extra valence electrons for anybody. Nothing's left over. Now this is called tetrahedral, which means it has 4 sides. It doesn't mean it has 4 hydrogen. It means it has 4 sides. And what it looks like in real life is it looks like this bent molecule, like a water molecule. But then you also add another bent molecule on top of it, okay? And when you do that, when you have a bent molecule and then you have another bent molecule on top of it in a different plane, then all these guys are spread out as far as possible. These two and these two are, look how far apart everybody is. And it ends up making a triangle on 4 different sides. And yeah, my model is kind of bad, but hopefully you can see where I'm coming from. And let me ask you a question. If I built this perfectly, would it be polar or nonpolar? Would you be able to tell that I had turned it at any point if I'd have built it perfectly? No. So it's tetrahedral nonpolar. And if I ask you if this is 2D or 3D, you'd say it's obviously 3D because it sticks up in the air. Now the last shape that you would need to know would be octahedral. Okay, and that means it has 8 sides. Now to end up with 8 sides, you don't have 8 valence electrons. And one that I like to draw when I'm drawing octahedral shapes, I like to draw SF6. And you may say to yourself, well, this doesn't add up. This -2, how can it have 6 fluorines? Well, that's not how covalent bonding works. We don't cancel them out. They're not neutral. So sulfur can end up with 6 fluorine atoms around it. And you end up 2, 4, 5. Pretend to put all these dots on here. I'd have to draw so many more dots. But what happens is you end up with this sulfur surrounded by 6 fluorine atoms. And what would that look like? It would look like this. And you would have 6 marshmallows or atoms sticking out, and they're all spread out. What are they trying to do? All 6 of these would be, that's right, they would be staying as far away from each other as possible because they all are surrounded by negative electrons. and then you end up with 8 sides. Okay, you would end up having 8 triangular sides. And 1, 2, 3, 4. See, I'm trying to stand up. 5, and I know my model's bad. But let me ask you a question. If you saw this, and these are all spread out evenly surrounding the central atom, do you think it'd be polar or nonpolar? That's right, it'd be nonpolar. And just for fun, let me ask you a question. Would something that's stuck up like this in the air, would it be 2D or 3D? That's right, it's 3D. And one more time for review, if it's FS6, how come we call it octahedral when there's only 6 of these out there? That's right, because it has 8 sides. Okay, good luck, people. Good luck.